Welcome back. Now that we have entered this last week of this course, let us take a review of what we have learned, and then we will look at some further directions in which you can take a look at combinatorics for advanced studies. As well as I will try to introduce a couple of topics with very short introductions. So we started our course with a look at PTN-Hull principle. Now, this was one of the most basic principles, one of the most trivial idea to come up with, and still one of the most powerful. And the power of PTN-Hull principle comes from the fact that because of its simplicity, it has such a wide range of applications. We looked at both the finite and infinite versions of this principle, and then so it has applications in several areas like analysis, graph theory, external combinatorics, geometry, term set theory, and we saw the connection of this principle with the theorem of term sets. Okay. So this was what we did first, and then we saw that it has many applications. And then we went to learn some basic counting techniques, right? So we learned the sum rule, product rule, right? And then looked at the binomial theorem and multinomial theorems, etc. We then went on to look at partitions and compositions of integers. Then looked at set partitions. And then related to this, we looked at Stirling numbers. And then we went to see, Stirling numbers can be stated or computed using recursions. And then we learned about recursions like Hemagenda recursion, Stirling recursions. And after that, we went to the principle of inclusion and exclusion. So what does this do? This is a technique where we try to count sets, but then we start with counting, a big over counting maybe. And then we say that okay, this is too much. So we are counting some of the things too many times. Then we do try to reduce them, and then we end up in under counting, right? And then okay, we try to do another counting, and then again end up over counting, and finally this kind of filtration, right? Several levels of filtration finally gives you what you want, right? And that is the principle of inclusion and exclusion. Now, even though this is how we see it, then we later realize that it's actually much more than that. It is actually a theorem from linear algebra, right? And then we saw that it can also be applied in posets, not just on the things that we're looking at, but it can be more generalized. And then we saw that there is a technique called Mobius inversion, right, which we can use. You can define associated to the poset, we can define Mobius function, and then using that we can do this kind of things. And principle of inclusion exclusion is just a special case of that. After this, we went to the powerful method of generating functions, right? So generating functions are basically representations of or encodings of, let's say, finite or infinite sequences of or counting sequences, basically, for our purpose of counting. But it could be more than one. And then this power series representation, and we said that it's a formal power series because we don't worry about whether the series converges. But we then say that okay, whenever it converges, we can generally write it to a nice function, and this function can be used to retrieve the data that we want whenever we want in a much more easier way. And as part of this, we learned that we can look at several types of generating functions. We started with the ordinary generating function, right? Then we saw that in the formal power series algebra, we had defined products, composition, and several other operations. And these operations can have a combinatorial meaning, right? In the sense that if you take two generating functions and multiply according to the rules of the formal power series algebra, then one can ask what does it mean combinatorially, and then we can define combinatorial object as related to this, and this in turn can have many applications in simplifying our computation. Then we said that okay, sometimes ordinary generating functions will not do because the series might be growing too fast. In that case, we said that okay, we can look at other techniques to simplify this by looking at things like exponential generating function, right, where we normalize or reduce the coefficients by multiplying the coefficient of x raised to n by n factorial. And then we saw that okay, this also, right, one can talk about this kind of generating functions, and then what happens combinatorially when we take the product or composition, etc. Now, of course, one should also keep in mind that these can be further generalized, like instead of exponential generating function, we can talk about maybe doubly exponential generating function or things like that, where if the function is growing even and the coefficients are growing even faster, we can divide by, instead of n factorial, we can divide by things like n factorial squared or higher powers and things like that. Now these are all valid techniques one can do, and we can also think about what happens when we take products, etc. That is for later. Then we saw as an application for the generating functions, we proved the very famous theorem by Euler, Euler's pentagonal number theorem. Now, we then went to look at a short visit to graph theory, where we did a quick overview of the basics like connectivity, trees, etc. Then we used the counting questions, looked at the counting questions on this. And then we took a short introduction of graph coloring. And then we went to look at Menger's theorem, which we proved using some graph theory techniques. And then we said that okay, Menger's theorem is basically equivalent to several other famous theorems from combinatories like Koenig's theorem and then Hall's theorem of system of distinct representatives. So what was this Hall's theorem? It says that it talks about the existence of unique representatives for a family of sets. Right? You can find it if every element was and every subset of the family. I mean, the union of all the elements in the family, the universe, had at least that many representatives, right? And that many sets in which to represent, then we can find a representative for each of the sets. Now, then we looked at planar graphs, and in particular, we learned a technique called discharging method, which is quite useful and which was used to prove the famous four-color theorem. Right? That is how the method became very famous, and people realized the potential of this method. We then looked at some group actions on objects like permutations, and then we said that okay, this group action is basically associating certain on sets in general, and then we said that okay, group actions by permutations is what basically all group actions reduces. Right? And then we looked at the action of permutation group and subgroups of the permutation group, right? The symmetric group. Because symmetric group represents a set of all permutations of S, and therefore any such actions can be encoded by a suitable subset of subgroup of the symmetric group. Then this was where we saw that the Folia's theory of counting, that this can be used to count, for example, coloring questions where we have some kind of symmetry acting, like when we have some objects where we don't want to look at all possible colorings per se, but we want to look at colorings which are non-constant, right? I mean non-isomorphic under the action of the symmetric group, or like under, for example, under rotation, etc. And then we learned Burnside's lemma and Folia's theorem. Then finally, we took a very quick look at what is called the species of combinatorial structures, where the species is basically like we have we divide the objects into certain classes, and you look at all possible finite objects that you can make out of all possible finite sets, and then we call this as a species. And then we saw that this species is basically very much related to the generating functions and Folia's theory. For example, we saw that there are three associated series that we can define on species generally. Right? The first one is the exponential generating function, which counts the labeled objects. Then we saw the ordinary generating function, which counts the isomorphism classes of, right? So isomorphism types. And these two can all be obtained from looking at the cycle index series, which is associated with the species, right? Which we can obtain using the ideas from Folia's theorem. So this is how we obtain the cycle index series, and then this the look of this combinatorial objects species is basically coming from the category theory, right? And then this was and this enables us to reduce the computations in many ways. For example, several of these objects one can see if you look at it as just figures or pictures of representations. We can see the relations between several of these objects immediately, and this gives us several new proofs, right? Simpler ways of finding proofs for usually difficult counting questions. And we saw some applications of this, and we also saw that we can define other operations like taking derivatives or pointing and all this can have a combinatorial connection. And of course, we just took a very quick introduction to this. It takes much more to look at this in detail. Okay, this is what we learned in combinatorics, and we saw several real-world applications of things, the techniques that we have learned in other areas, at least a few of them. Now, so that is what we learned in this course so far. But now let me introduce a few advanced topics, courses that you can take from later, or at least things that you can read on your own related to combinatorics. There are several areas of combinatorics now, and what I'm going to do is to present a list of them, and then introduce a couple of them, and then that's where we stop. Okay, so here is the further directions. So here is a list of advanced topics in combinatorics, like which comes to my mind immediately. Right? There are many more, and these are some of the interesting techniques and specialized areas. Let me start with the first one, which is called the linear algebra method. So what is the linear algebra method? This is a technique in combinatorics where one uses the ideas from linear algebra, where we have vector spaces, then associated we have dimensions, and then we know that the subspace must have dimension less or equal to the dimension of the space. Then we have matrices, right? Their properties, and like for example eigenvalues of linear operators, and several tools from linear algebra are there, and these can be used quite effectively in obtaining proofs for many combinatorial questions where we don't really see a nice combinatorial proof. Of course, combinatorial proof can be very illuminating in the sense that it can give several other insights which we may not get using techniques like algebra related techniques. But then when we don't have a nice combinatorial proof, then we have to necessarily look at other techniques, and this is a very powerful technique, and we will look at least a couple of examples from linear algebra method, and even though it's just a very few short half an hour introduction, I will give you a short look at this. We will not go into like eigenvalue and spectral theorems, etc. For this part. This is just a quick introduction. But then second topic that I want to introduce you is that of probabilistic method. So what is probabilistic method? Again, probabilistic method is a very powerful method in counting, in combinatorics, where we use the ideas and tools from probability theory, right? Just like the linear algebra method. Here we use the tools from probability theory to show the existence of objects, or like actually come up with objects. And it may be kind of counterintuitive, but the idea of probabilistic method is very nice and simple. That suppose one can show that we want to see whether certain types of combinatorial objects exist. For example, given a graph, I want to know whether there is a particular type of coloring of this graph using at most, let's say, 100 colors or 20 colors. Now, it may not be practical to look at all possible colorings to find out this, because the number of colorings usually grows exponentially large in terms of the size of the object that we are looking. Now, if we have like several colors, and then we have several vertices in the graph, right? Several vertices and edges in the graph. Usually, it's not practical to do. Even with numbers like close to 50 or 60, we will be at loss. So, what are the other things that we can do? Because our brute force things is not going to work. They are very powerless when the size grows quite large. So one can do the following: that suppose you want to show a certain type of object exists, right? Then all you need to show is that there is a positive probability for this object. And this is like kind of surprising, right? But this was observed, I think, first by Paul Eldridge, and what he said was that okay, now to show a certain kind of thing, object, object, combinatorial object exists, all I have to do is to show that with non-zero probability, right, this object exists. Because if I can show the probability is non-zero, at least one object of this type must exist. Otherwise, I will not be able to show non-zero. I can say greater than or equal to 0, but if I show strictly greater than 0 probability, then that is because at least one of them is existing. And this idea is very powerful, and there are many associated tools from probability theory we can use. For example, we can use just the linearity of expectation, or just the union bound of probabilities. We will see what this is, and then we will be able to use some further advanced tools like let's say Chernoff bounds or Lowa's local lemma. Then several concentration results from probability theory like Azuma's lemma, etc., can be used. Telegrams inequality. All these can be used to prove very powerful results in combinatorics. Of course, we will not go into most of this. We will just look at a couple of examples, from using union bound and maybe linearity of expectation, and then leave the later things for an advanced course for people who are interested. The third thing I want to tell you about is another very powerful technique called polynomial method. Now, the polynomial method, as the name suggests, uses polynomials and related tools from polynomials. And a couple of things I want to emphasize here is one is that of the results related to algebraic result called Hilbert's Nullstellensatz. So the Nullstellensatz basically, it's a German word which talks about the location of the zeros of a polynomial. Now, when we have this results, Noga Allen, a famous mathematician from Israel, so he figured out there is a combinatorial version of the same result that is possible. Okay? So the combinatorial Nullstellensatz basically tells about again, like when you can show certain kinds of zeros or roots of the polynomial exist or not. And this is a very powerful tool, especially in graph coloring and many other topics. In fact, if anybody is interested, they can look at the first paper on this by Noga Allen, which is available from this webpage, on combinatorial Nullstellensatz, where he proves this result and then he uses it to prove more than a dozen very important and very famous theorems that has been proved earlier, many of them, in a much simpler way. Just looking at certain polynomials, right? Define a polynomial associated to this question, and then use a polynomial and Nullstellensatz to show certain kind of structures must exist. Then another associated tool is that of incidence theorem, and this incidence theorem especially came into fame because quite recently, I think in 2009 or something, a very young mathematician called futher used it to prove some very long-standing, and supposed to be difficult questions, and gave a very short proof, like just a page or half-page proof for these results using some incidence theorem and again polynomial method. And basically, the polynomials are used to give some kind of polynomial interpolations are used to give some kind of restrictions to the algebraic structures that we are talking about, and then that will help to and I know because this algebraic structures has a geometrical shape, and then you can talk about the combinatoric. Basically, it has some kind of structure where you can talk about the vertices and edges, spaces, etc., and many other related things. For example, we are talking about the lines, right? Intersecting lines and other shapes, and then you can talk about the number of them, right? And you can talk about the number of extremal points and things like that. So these are the tools from polynomial method. There are several more which we will not look at in this course, but I just wanted to tell you about this. Then there is, of course, advanced graph theory, where many many courses can be done. There are several directions in which one can go. For example, spectral graph theory, then algebraic graph theory, and algorithmic graph theory. Because of the advent of computer science, graph theory has too many branches. Again, we will not go further into this. I will for each of these topics, I will suggest some books one can look at, and if interested, one can look at further courses in this topic. And then there is extremal combinatorics, which talks about the extremal questions, like what is the maximum number of certain objects that can be there, like what are the other maximum properties, what is the largest object of this type, and such questions. There are several nice books, and it's a very important area. There are several nice books and topics on this. I will mention some of them. Then there is design theory. Design theory talks about the existence of special type of structures, like symmetric structures, or objects having very specific symmetries, or to partition objects into copies of certain types of objects. So all these questions, like for example, partitioning the edges of as a complete graph to copies of some other type of graphs. These kind of questions all come in design theory. And then we have the Ramsey theory. So Ramsey theory looks at basically order in disorder. Like we saw, when we looked at PGN principle, we saw the first result on Ramsey theory, the first Ramsey theorem, which basically talks about like, so you look at all possible coloring, right? I mean, any type of coloring, you allow let's say a fixed number of colors, and then we say that okay, you are free to give the color as whichever way you want, no matter how you are going to give the coloring. As far as the object is large, right, we say that we can find very specific very restricted type of colorings, very structured coloring, like basically a specific order in all this disorder, right? No matter how you are going to do this, you don't have a choice but to come up with such order, right? So when the number increases, right, even though there is chaos, there should be some order within. Like you should be able to find substructures with a specific order. In fact, all kind of orders. And you can. So the Ramsey theory is really huge because the type of objects that we are looking at can vary a lot. And then it's also very difficult. One of the most difficult areas in combinatory, because even for very small numbers, the very small size structures we are looking at, the numbers that we are going to talk about is extremely huge, and then there is no way of practically computing this or verifying this, and therefore only thing is to come up with theoretical arguments, and it makes it even more difficult, even because one cannot even try an experiment on a small object to see, right, what kind of things that you are coming up with. So it's a very difficult area. Then we have enumerative combinatorics. In fact, a large part of our course was enumerative combinatorics, and there are basically counting objects, right, using several techniques, and that's what we learned. And related to this, there can be many advanced courses, and I will suggest some excellent books on this. And another topic I want to point out is that of analytic combinatorics, right? Where one looks at objects from analysis and tools from analysis. For example, our some of the results that we used in generative functions, of course, comes from analysis. So therefore, it is essentially related to generative functions and all, but also other techniques like from analysis are used. And then, of course, one can also use combinatorics in the analysis part. And so therefore, these are interconnected. And there is at least one excellent book on this, which I know, which I will mention to you. And then, of course, there are other topics like now every branch has its own combinatorics. Like there is topological combinatorics, there is geometric combinatorics, and there are books on each of these. Right? Then one has other things like because combinatorics has relations to other areas like physics, chemistry. Right? So there, because physics uses a lot of combinatorics these days, like plane partitions. So we learned about integer partitions. We can now define higher dimensional partitions like plane partitions and higher dimensional partitions. And these higher dimensional partitions has direct applications into many physics questions like uh, uh, and therefore lots of physics people are looking at combinatorics, especially related to specifically to them. So there is combinatorics and physics. There are related topics and courses. I don't know about any book relating this, but there are several courses on this. And then, of course, combinatorics in chemistry and genomics. All these things are there. There are some books also on this, but I'm not much into this, so I will not give any references at this moment. But one can, of course, look at it. Okay, now let me wind up this entire thing by giving some introduction to the first two topics like linear algebra method and probabilistic method. That's what we are going to do in the next couple of lectures.